Hello everyone, welcome to the Algorists. In this video, we will be talking about Morris in order traversal, and this video is going to be the accompanying video for the Morris in order traversal content we have in the algorist.com. So let me show you the content first. So how you would go there. So if you searched the algorists, let's see where the website is. Yeah, it's in the first page of the search result. The algorithms are a platform to make you naturally good at algorithmic problem solving. Let's go there, and from there we will be going to the list of contents for algorithms and data structures. Let's go there, and from there let's see where the more traversal is. It is here. um, yeah, this chapter is not yet complete, as I have started to working on this one, and I'll be completing the chapter after um, I'm done working on the video. So let's see what this Morris in order traversal is all about. So the main motivation behind learning this algorithm is that the recursive and iterative way of doing in-order traversal, the traditional way of doing the in-order traversal in a binary tree, takes O of n space, where n is the total number of nodes we have in that tree. So traditionally, the space is order of n. We want to optimize the space complexity of in-order traversal while still keeping the time complexity the same. So the time complexity would still be order of n. So we want to optimize the space complexity from order of n to order of 1. So let's see why we why in the traditional way of doing recursive and iterative way of doing the traversal, why we have O of n space there. So let's take this tree. Yeah, so for our convenience, I just took a binary search tree. So we know what would be the outcome of the in-order traversal very easily, because we know for BST it is already in um, the ascending order, always in the it is always sorted. So how it works is, as you know already, um, we recurse from 10, then it comes to left 5, and then it comes to 4, then it 3. It sees that it has no left subtree here, so it processes this node, and then now here is why we need to recurse. And you will have to keep in mind, recursion is nothing but using a stack that is why while we implement the iterative way of doing, we implement that through stack. So this is why we need the recursion, then that is the stack data structure, and that is why we have order of n space needed. That is from 3, since it does not have any left and right subtree, and both of them are null. We have to backtrack from here to node 4, like node with value 4. And so when we do iteratively, we pop 3 from the stack, and so we see that on top of the stack we have 4. So that is how we backtrack to the parent node. And same for the recursion, of course. Like in recursion, uh, like also like the recursion call on the node 3 real like returns, and it is popped from the recursion stack, and that is how we land from 3 from node with value 3 to node with value 4, and that is what we say backtracking. So I think by now you got the idea. We need order of n space so that we can backtrack um, to the next node in the INORDER traversal. So in this case, the next node happens to be the parent node, but that is not always true. Like say here we know the traversal here would be 3, then 4, then 5, then 6, and then 10. So we see from 6 the next node in the traversal would be 10, but 10 is not its parent. um, like 10 would be the next node of 6, or I can say in a different way that 6 is the predecessor of 10, and that's the right way of saying here. We are like, because we are having to keep track of the nodes in the stack, because we want to know, like we want to come back from the predecessor. So when we are on 6, we want to backtrack to 10. Because by then, like since it is in order, 5 will already be processed and popped from the stack, and 6 will be on top when we are processing 6, and when we have processed the 6, it will be popped from the stack, and 10 will be at the top of the stack. um, so the the solution here is to have a link between the predecessor to each node, or put in a different way, for each node we should keep a link from that node to its predecessor. So how we can do is, when we are 10, when we are at 10, we need to see what the predecessor of this node is going to be, and visually we can say, like we can see here that the predecessor of 10 is going to be 6. We can also say that from the in order traversal result here. For 5, the predecessor is 4. For 4, the predecessor is 3. um, for 15, the predecessor is 11. So if we keep this link for every node, then we don't need to keep the stack just to keep track of which node comes next. Like for 6, the node with value 10 comes next. Just to know this, we need to keep these nodes in the stack. But as you can see here, if we keep this like this dotted links, which goes from the predecessor to its next node, then we don't need to keep any stack, and that is what brings the space complexity from O of n to O of 1. I mean constant space. So let's see like how we can do it. So for any node, like say for the node with value 10, the predecessor node would be node with value 6. So let's discuss how we can find the predecessor node for each node. So if you um, observe here, the predecessor node is always the rightmost node of the left subtree. So for a node with value 10, the predecessor node is the rightmost node of the left subtree. So the root of the left subtree is the node with value 5. The rightmost node of the subtree rooted at the node with value 5 will be the predecessor of the current node, and the current node is the node with value 10 that we are talking about here. The same is true for all other nodes. For 5, the predecessor is 4, and that is actually the leftmost node. Sorry, I mean the rightmost node of the left subtree. Since 4 has no right child, so its right child is null. So 4 itself is the rightmost node in the subtree rooted at the node with value 4. For 15, um, the left node is the node with value 11, and it has no other children. So this node itself is the rightmost node of the subtree rooted at 11. So that is how 11 is the predecessor of the node with value like 15. Um, so from our discussion we already got an idea of how to convert our thought in our code. So we are talking about the current node, and so the current node will initially be the given root, and then we'll have to compute the right most child of the of its left subtree, and then we'll have to change the pointer of the predecessor on the, and how we can do is we can so the predecessor, if you have noticed, will always have both the children as null. So how we can do is we can change the right pointer of the predecessor, and we can point to the current node as and we can point its right child to the current node. So our current node is the node with value 10, and the predecessor we computed is the node with value 6. We will point the right child pointer of the node with value 6 to the current node, and the current node is the node with value 10. So yeah, and this will be done only if the current node has a left child, because if the left child is null, then the current node is the leftmost node of the subtree rooted at the current node. So we just to process that, and we move on to the right child of the current node. So let's start writing the algorithm for the Morris INORDER traversal, and then we like we will see if the algorithm that we are coming with actually works or not. So let's take our method name as Morris INORDER, and say let's we want to just print on all the node values. So we will start with taking a node as current, and the current node will be root. And while the current is not null, so if you see the last node in the traversal here, it will be 11, and 11 will have no left child, so it will search for its right child, and it will make the right child as 15, and 15 we will also have to modify, so that like that is like something I missed. In order to avoid having an infinite loop, we need to change the left child pointer of the current node, and like this needs to happen for every node, because if we don't remove the child node of 10, then when it comes to 10, it will start processing the its left subtree again. So what we will do is, we will after we change the right child pointer of the predecessor to the current node, we will delete the previous left child pointer for the current node, being like, because by that time this this whole left subtree will be processed. So as I was saying, at the end of the processing, like when we are in the node with value 15, the left pointer will be null, so it will make the right child as current, and we will see that the current is null, and that is how we would know that we have processed the whole tree, and we need to stop the processing. So we will run the loop till the current is not null. So if we don't have a left child, we have nothing to do with the left subtree there. We have because we don't even have a left subtree, so we should just process the current node and move on to the right. And for us, processing means just printing the value. So we process, and then we move on to the right. So current becomes current dot right. Yeah, like just think about a tree like this. Say we have 10 here, we have up to like 20 here, we have 15 here, and we have say 24. If this is the given tree and we are at 10, so 10 is the leftmost value of the in order traversal, so there is nothing to process on the left subtree, so we just process it and move on to the right. Okay, so so this would happen if there is no left child. And if there is, then what do we need to do? We need to get predecessor, then so we will write a method like just to get the predecessor, but as of now let's assume that we already have the method that gives us the predecessor. So node pre equal to get predecessor of current node. Next, what do we need to do? So say we are at 10, we computed that 6 is the predecessor. We need to do two things. We need to change the right child pointer of the predecessor and point it to the current node, and we also need to delete the left pointer of the current node and make it null. And so now this is the current node. After we have done these two operations, we need to make the left child the current node, because this is in order. So we we need to go towards the left, and for each node we need to do the same thing, depending on whether it has a left child or not. So let's do that. So pre right equal to current now I'll have to make the left child null of the current node, but I would also have to make the existing left child of the current node as the next current node. Well, I mean as the next value for the current node. Like, so the the reference of the next should point to the left child node of the current, um, which means we need to take a temp node and point that to current, and now current equal to current dot left, and now you would see why I took the temp. So temp now points to the previous current, because now current points to current dot left. So we have the previous current in the temp, and I'll just change the left to be null. So we have left out the implementation of how to get the predecessor, and we will do that right now. So in order to get the predecessor, we need to grab the rightmost child of its left subtree. So left subtree root equal to root dot left, and we need to traverse all the way to the right. So we will traverse all the way to the right, and we would stop only when we see that the right pointer of a node is null. That is how we know that we have reached the rightmost child of the left subtree. So what I would do is I would actually name this one as current current right return. Yeah, so this completes the whole algorithm of the Morris traversal. So let's see if the code we wrote works or not. We are at 10. It has a left a subtree. So we compute the predecessor. We point the right child pointer of the predecessor to the current node, which is the node with 10. We make the left child um, pointer of the current node as null, but before that we make the left child of the of the current pointer as current. So the current pointer is 10, the left child is 5. We make the node with value 5 as current, and we actually make the left pointer as null after doing this operation. So now we have 5 as the current. um, we see that the 4 is the predecessor. We point from 4 to 5 as the right child of 4. We make 4 the next current. We delete this left link, and we do the same. When we are here at the node with value 4, we compute the predecessor, and we see that the node with value 3 is its predecessor. We make the right child pointer of the node with value 3 point to the current node, which is 4. We keep the node 4, the node with value 4, which is the current node, in a temp node, because we need to make the left child of the current node as the next current. So the node with value 3 will become the current node, and then we come back to the temp and we delete the right child pointer for the temp node, which is actually the previous current node. So now we are at the node with value 3. We see that it has no left child, and when we don't have left child, we just process that node and we move on to the right child. So we print its value so here by processing we mean just printing its value. So we print its value and we move on to the right child, which is 4 here. Now we see what is so we look at the left child of 4, and we see that it is null because we have already modified the left child pointer and made that null. So if so when the left child is null, we just process that node and we move on to its right child, and we have already modified its right child and made that point to the node with value 5, because 4 was the predecessor, 4 is the predecessor of 5. So we process from the node with value 4 and we move on to its right. child, which is 5, and we do the same thing for 5. We process 5 because it has no left child, as the left child was modified and was pointed to null. We go to a its left, so since the left child of the node with value 5 is null, we move on to the right child, which is 6. um, 6 has no left child, so we process 6 and we move on to its right child. And like this is how we actually come back to the root of the whole tree, which is 10. um, so the left child has been made null, so we process 10, we move on to its right child, which is 15. Now 15 um, has its left child. So we try to find out the predecessor of 15, and we see that it is 5 and it is 11. We point 15 from here as its right child. We make 11 the next current, and we delete the left child of the previous current, which is 15. So 11 is the new current. There is no left child, and the right child is 15. So we process 11 and move on to its right child. The right child has no left child, because we had modified the pointer, so we process 15 and we move on to its right child and make that current, and we see that the right child is null. So so now the current is null, and the whole process ends there, the while loop ends there. So we see the Morris algorithm works perfectly fine. It gives the correct in order traversal result. But the biggest advantage we get that we are doing this in constant space. So I will have this code in the website. Me take a method. I'm taking void because I will be just printing the value of the node. You can even take a list or some other data structures if you want to store the value in a data structure. But for this exercise, I will be just printing the value of the node. um, Get print in order. Let's quickly define the node class. So first of all, we need to do a null check for the given root. So we will only do the traversal if root is not equal to null, and then let's make root the current node. Okay, so now let's see how we are going to implement this algorithm. So what if the root has no left subtree? Then in order traversal, that would be become the we would print that node first, because in order traversal we first traverse the left subtree, and then we visit the root, we print it, and then we traverse the right subtree. So if we don't have the left subtree, then we have no subtree to traverse. So we visit the current node, which is the root, we process it, and here processing means printing, and then we move on to its right subtree. So we will do the traversal till the time the current node is not null. So as we discussed, if current node has no left subtree, so the left is null, we process it, visit and process, no left subtree to traverse. Out there, print let's just to print, we will do have. And what's next? We visited, we printed the value, and we now need to traverse the right subtree. So we would make the right child of the current node as the current node. And if we have a left subtree, then what? We just discussed that the in order predecessor is always the rightmost child of the left subtree. So when we have the left subtree, only then creating the threaded link comes into play, because we create the threaded link by modifying the right child of the in order successor. So if we don't have our left subtree, the question of having an in order predecessor does not even come into play. So now that we have left subtree, we would find the in order successor, and we would create the threaded link, which would actually help us in optimizing the space complexity from worst case order of n to constant space. So let's do that here. So node in order predecessor equal to I will create a method to find the predecessor. Say let's say that method name is get. So let's implement that method first. Obviously this would real like return a node. It will return the in-order predecessor like which is of type node. So how do we compute the in-order predecessor? In-order predecessor is the rightmost child of the left subtree. So we would have to go, so the node for which we are computing its in-order predecessor, we need to go to its left child, and then we will have to traverse all the way to the right, like right from the left child. So we will have to follow the rightmost path, the path that leads us to the node that is at the rightmost position in that subtree. So let's first, so we are making the left child of the input node as the current, and we will have a while loop. While, like we will loop while the right child of current is not null. So we traversed all the way to the right until we got a null node. So when we are out of the while loop, the current node is such that whose right child is null. So the current node is referencing to the rightmost node of the left subtree of the given node, which is the in-order predecessor of the given node. So we got the in-order predecessor. So now what we need to do is we need to modify the right child pointer of in-order predecessor to point to the current node. So what we do is in-order predecessor dot right equal to current. So this is the threaded link concept from binary from threaded binary tree. And this is what helps us to avoid having stack and backtracking. So now that we computed the in-order predecessor for the current node, we definitely need to go to its left subtree because we haven't processed the left subtree yet. So we cannot print value of the right of the current node. So we should move on to its left child so that we can process the left subtree, and then we come back to the current node and actually visit and print the value. So the current becomes current dot left. So definitely we need to keep the current in a temp node. So node temp equal to current, and which is very important here, we need to modify the left child pointer of the current node and make it null. So that is how we would know that the left subtree for that node has already been processed. So we would make left equal to null. Yeah, so the purpose of doing this is when we come back to this current node by following the right child pointer of its in-order predecessor, we need to check if the left subtree is null or not. So if we see that the left subtree is still pointing to the previous left child, then it will become an infinite loop because it will come here, it will see that the left child is not null, so it will come in the else block and it will go on doing the same procedure again and again. So in order to prevent infinite loop, we need to change the the left child pointer of the current node as well. So this is one of the tricky part here that we need to do in order to achieve the threaded binary tree concept here and actually achieve the space complexity optimization. So let's see if we are getting the correct result by running this code. So let me take one tree which I have been already using in a different code in a different class. Yeah, so for this node, let's see what our expected result is. So 40, then it will be 20, then 45, then 90, then 10, then 30. Okay, let's see what we get by running. Yeah, so 40 followed by 20 followed by 45 followed by 90 followed by 10 and then 30.